Okay, here we go. So you guys thought you were done with rotations about axes, didn't you? Not the case. So today we're going to talk about the area of a surface of revolution. And these are just a bunch of silly formulas. Um, don't really worry about them. I'm going to use them and show you how they work. They're just here for you to have reference. Both of these equations right here, this one and this one, are rotations about the x-axis. It's just depending on what bound you're using. You see that, how this is in terms of y bounds, and this one is in terms of x bounds. Okay, so the a and b here would be x values, the c and d here would be y values. And then instead of doing it that way, your book, to make the formula easier for you to remember, typically writes it this way. When you rotate about the x-axis, it's going to be 2 pi y ds. When you go about the y-axis, it's going to be 2 pi x ds, where ds is either one of these. Okay? And how you determine which one of these you use is based on the bounds. Okay? So finding surface area, and like I said, I'll show you. 2 pi y and 2 pi x, those are the circumference, correct? And the ds for each one of these is simply the arc length. Are we okay with that?
Yeah.
That makes sense to you guys? Okay. So that's important for you to get. And remember, your ds is determined by the bounds in which you're going to use. Okay? So just so we quickly understand some stuff, I'm going to do some little kid sketches here. So if I have a function and I'm going to rotate this about the x-axis, right? I know that the circumference is going to be this. This is going to be the radius, correct? For the circle that's created.
Yes.
So this would be my y distance, right? That's how far I am away. And so the circumference, the circumference here is going to be 2 pi y, right? And then since we're rotating about the x-axis, my surface area integral is going to be 2 pi y ds. Okay? If we have a picture that looks like this, ooh, that's terrible. That's a terrible drawing. Forgive me. Now here the radius is going to be this distance, correct? Oops. Correct? And so that radius is going to be x. And now my circumference here is going to be 2 pi x. And since I'm rotating, about the y-axis, and that makes sense that I'm rotating about the y-axis here, correct? Because my function, just in case you don't see it, is this. This is the function here. I don't know why that's showing up like that. And here's my function here. So does that make sense about the rotation then?
Yes.
Okay, and then I'm going to get s is equal to 2 pi x ds. Okay, so it's imperative when we do these problems that we're able to see and make our graphs so we know which way to do our slice. Okay, so let's look at an example. And I cheated and took this example out of the book because they had a nice picture for us so that we could see. And really, I could clean it up a little bit so you can see it even better. If you want me to do it in 2 dimensions instead of this 3-dimensional rotation, it would look something like this, right? So if I had this, my function would have been something that looks like this, and then like this, and then we have our does that make sense? But this is the function here, right? That's the function y is equal to the square root of 4 minus x squared. Do you all agree with that?
Yes.
Okay, and the bounds here are from -1 on x to 1 on x. So because of that, that dictates which formula we should use when attacking this problem. Oops, need my notes. So that we're consistent, I want to be able to show you. So since we're rotating about the x-axis, this is my radius, correct? And that radius is in terms of how high it is. So this would be a y, right?
Right.
Okay, just making sure you guys are tracking with me. Okay. So then I know that the formula that I'm going to use is going to be, the surface area will be the integral of 2 pi y ds, but the ds that I'm going to choose here is dictated by the bounds, and so the bounds are in terms of what?
-1 to 1.
Yes, but what are they? Or is that an x or a y?
X.
It's an x. And so my ds is going to be in terms of dx. So I'm going to go, and this is where some of you will trip out. It's going to be 2 pi y root for the arc length, 1 plus dy dx, quantity squared dx. Right? Now, I'm going to do some side work just to make this clean for me. I know that y, since I'm doing it in terms of x, I don't want to do implicit differentiation and whatnot. So I can substitute for y, can't I? What is y in terms of x? The original function. Y is what?
Square root of 4 minus x squared.
Right. So then I'm going to break this up and become the integral of 2 pi radical 4 minus x squared. And then over here, 1 plus. But now I need to know what the derivative is. So when I take the derivative of that y, I'm going to get negative x over the root of 4 minus x squared. Do you agree with me?
Yes.
Okay, that's just the derivative there, right? So then when I square that, I'm going to get x squared over 4 minus x squared dx. Now, what were my bounds?
-1 to 1.
So I'm going to go from -1 to 1. Okay, so it's circumference with arc length to be able to get the surface area of this rotation that we're having. Does that make sense? It's the circumference, right? How we're going to get around, times the surface area, or I'm sorry, the arc length, to be able to just get the surface area of this thing. We don't want what's inside. We don't want a solid. We only want the outside piece. Does that make sense? From chapter 6, we did rotations of solids. Now what we want is only the outside ring. And so that's arc length with circumference that's going to give us that. Are you guys tracking with me?
Yes. Yes.
Okay, good. Then I'm going to do, it's some algebra here. So I'm going to go, oops. The integral is going to go from -1 to 1. I'll pull out the 2 pi because that's just a constant. I'm going to get root of 4 minus x squared, root of 4 minus x squared plus x squared over 4 minus x squared, and this should all be rooted, dx, which is going to give me 2 pi integral from -1 to 1 of root of 4 minus x squared, root of 4 over 4 minus x squared dx. I'm trying to be deliberate with my work for you so you can all see. 2 pi from -1 to 1 of root of 4 minus x squared times 2 over root of 4 minus x squared. Isn't that wonderful? What's going to happen to my roots?
They cancel out.
Yep. They're going to cancel, so I'm going to get 2 pi from -1 to 1. In fact, let's just call it 4 pi dx. So that will yield 4 pi x evaluated from -1 to 1, which is going to give me 4 pi times 1 minus a -1, which is 8 pi. And this should be units what? What kind of units are those?
Squared, because surface area.
Perfect. It's units squared because of surface area. We all right?
Yeah.
Yes. Yes.
All right. It really isn't too bad, especially if you have a solid foundation on volume rotations and whatnot, but it's really, really not that bad. And in this case, our ds was the 1 plus the derivative squared in terms of dx, and it was because our bounds were in terms of x. Okay? So does that make sense how you decide which ds you use?
It's
Yes.
the opposite of whatever one you're in, right? Because this one was in terms of x, so we did dy over dx.
So yeah, whatever the bounds are. So I'm going to show you that if you have both bounds, you'll get the same answer regardless of which way you do the integral. But what's imperative is that we have the correct radius, okay? So let me show you this. So in example 2, we're going to have our x bounds and our y bounds. So I can attack this one using ds in terms of dx or using the ds in terms of dy. Okay? So looking at this problem, the radius, because we always want to find the radius is going to be, since the rotation is about the y-axis, this is my radius, correct?
Yes.
Okay, since that's my radius, shouldn't that be an x?
Yeah.
Right?
Yes.
That's some x distance. And so what's going to happen here is I'm going to get, okay, my circumference trying to take you guys through the reasoning that I'm doing, is going to be 2 pi x. Yes?
Yes. Yes.
Okay. So since I'm going this way, I'm going to go my surface area. My surface area is going to be the integral of 2 pi x, and then my ds, I'm going to use the bounds that are the x's. So I'm going to go from 1 to 2. Are you guys there? So, can you guys hear me? Can are you guys there?
Yeah. Yes.
Yeah, we can hear you now.
Okay, I don't know what the heck. I got bounced.
You're back.
Yeah, that was weird.
We
Sorry about
honestly thought
that.
it was our connection, and we were like, what happened?
Yeah, thank God you guys didn't get booted from the session. I'm still recording, which is great, but I had lost you guys. I'm like, wait, where's my class? So thank God you're still here, even though there's only 10 of you, but you're here. Sorry about that. Okay, so my ds here, since the bounds are going to be in terms of x, it's going to be the root of 1 plus dy dx, that quantity squared dx, right?
Right.
Okay, so now what I need to do is I need to go, okay, y is x squared, so dy dx is 2x. Yes?
Yes.
So when I do this, I'm going to go the integral from 1 to 2 of 2 pi x root of 1 plus 2x squared dx.
Got it.
Okay, then from here, I'm going to get s is equal to the integral from 1 to 2 of 2 pi x root of 1 plus 4x squared dx. I'm going to pull out my 2 pi. And the technique for integrating this would be what? Anybody?
Would it be an a plus x squared, like where it's a
trig sub?
trig function? Yep.
Well, no, because, I mean, you could do it that way, but then you have a product there. So then you'd have a UV. We don't want to do that. Isn't it cleaner to do this one with a U sub?
Yes, you said. Yeah, you're right.
So the U sub here would be U is 1 plus 4x squared. So du would be 8x dx. See how that would take care of the x here and the dx? So I'm going to get 1/8 du is x dx. So my integral is going to go pi over 4 integral of u to the 1/2 du. And I'm going to change my bounds because I don't want to deal with the bounds anymore. So I'm going to get 5 and root 17, correct?
Correct.
And that's going to give me pi over 4 u to the 3/2 times 2/3, right? That's going to multiply. Evaluated from 5 to root 17. And that's going to give me pi over 6, 17 root 17 minus 5 root 5. And obviously, units squared.
And the limits of 5 and root 17 came from the u, right?
Yes, correct. So what I did for the limits is I plugged in 1, so I got 4. So 1 plus 4 is my 5. And then I plugged in 2. 2 squared is 4 times 4 is 16 plus 1 gives me the 17. Oh, I don't know why I put root 17. Silly me, that's a mistake. This should just be 17. Not roots is 17. My bad. We okay?
Yes.
Okay. Now, if we wanted to do this problem knowing that the bounds were y's, we could do it with the bounds being y. So now our ds would be in terms of dy, correct? So let's see if I have enough. I think I have enough room here to do it this way. So by doing this exact same problem, I'm going to do it now, though, with dy's. So my setup is going to be s is equal to the integral of 2 pi x ds. But what I'm going to do is I'm going to say s is from, the bounds were what? From 1 to 4, correct? Of 2 pi x root of 1 plus, now it's going to be dx dy squared dy.
So would we still be using 2 pi x, or would it be 2 pi y?
You'll see in just a second. So our function was, our original function was y was equal to x squared, correct?
Correct.
But since we're in terms of dy, we need to change anything that's in terms of x to y. So this is going to become root of y is x. Agreed?
Agreed.
So we can see from there then this is going to go from 1 to 4 of 2 pi root of y, root of 1 plus, and now I need the derivative of that. So my dx dy is going to be 1 over 2 root of y. Agreed?
Agreed.
So you notice the circumference didn't change. I just changed the circumference, my radius, from x's to y's. Does that make sense? So then I'm going to simplify.
Yes.
I'm going to simplify this for you guys. So s is going to be integral from 1 to 4. I should put the 2 pi out already. Root of y times 1 plus 1 over 4y dy. We'll come up here with this. So my s is going to be equal to 2 pi root 1 to 4 of root of y root of 4y plus 1 over 4y dy. Correct? In fact, let me clean it up. Let me make it even cleaner than that. There's a algebraic manipulation I can do. It's better. You'll see this. If I multiply the two radicals together, don't I get y plus y over 4y dy?
Yes.
That's helpful because when I go to clean this up, I'm going to get y plus 1/4 dy. And now I'll do the multiplying by 4. So I'll get 2 pi root of 1. I'll get a 1/2 4y plus 1 dy. Does everyone see how I got that step right there?
Yes.
So that's going to give me 2 pi 1 to 4 of this, and then we're going to do a u sub, correct?
Correct.
So my u here is going to be 4y plus 1, so du will be 4 dy, so 1/4 du is dy, so that's going to give me pi over 2, and then I'm going to just integrate it, if that's okay with all of you. Or here, I'll set it up just so you guys can see. 5 to...
That's the 1/2.
What's 1/2 times... oh. Yeah, this should be gone. Thank you. So from here, I'm going to get u to the 1/2 du, and we can see that this is exactly the same I forgot the over 4. This is exactly the same as the previous problem, right?
Right.
So we see that the answer is going to be the same. So depending on what the bounds are, you're still going to find your radius how you would. It's just the bounds will dictate whether you want to do it in terms of dy or dx. Okay? Does that make sense?
Yes.
Okay. Always with these problems, though, always with these problems, the radius is going to be from the axis of rotation. So if this is the axis of rotation, this is the radius. If it's parallel to x, it's an x radius. In this one, we see the rotation is this way. The radius is this way. It's parallel to y, and so it's a y radius. Okay? And then I can put the answer if you'd like. The answer ends up being pi over 6 17 root 17 minus 5 root 5, which is the same as before. Any question? Just trying to absorb.
Yeah, I think it's good.
David, were you trying to say something?
Yeah, I was trying to say if the 17 on the integral is supposed to be square rooted.
No, it's not. So up here, I corrected it. See how it's not square rooted anymore?
Oh, okay, okay.
Yeah, I had messed up and put a square root there. Silly me. There shouldn't be a square root there.
Yeah,
Okay?
I was wondering. Okay.
All right. So far with the first two, I provided you with pictures from the book. This third one, I'm not going to give you a picture, and so we need to be able to graph it, correct? So we see that the bounds are from 0 to 1. So our ds is going to be in terms of what? The derivative of the surface area should be in terms of dx or dy? Did you
dx.
dx,
It
yeah.
should be dx, right? Because the bounds that we have are in terms of x, so our ds should be in terms of dx. Okay? We all know how to graph e to the x, right? So we know at 1 and then it's going to explode this way, correct? We know that the rotation is going about the x-axis, so it's being rotated this way, and so we see that this thing's going to look something like this, right? So then our radial slice is going to be this one, right? And since our radial slice is that way, what's it going to be? What's the radius going to be in? Isn't that a y? Right? Andrew got it, right? It's a y. So then I know that the circumference of this problem is going to be 2 pi y. Right? So,
Right.
So just the setup of this thing, it's going to be s is equal to the integral. We know it's going to go from 0 to 1 of 2 pi y root of 1 plus dy dx squared dx. Ready-o? Are we good?
Yeah.
Yes.
Okay.
Yes.
Cool. Okay, so then from here, we don't want that y to be there. We want it in terms of x, right? And so the function told us that y was equal to e to the x, so we can change that to be from 0 to 1 of 2 pi e to the x, right? Root of 1 plus the derivative of that is going to be dy dx is e to the x, which is going to give us e to the 2x dx. Right? And then here comes a problem that's going to take about 45 minutes to do. You think I'm kidding? This problem is a lift. So the calculus piece to set this up to be able to do the rotation to find the surface area, we're done. We did it. To find the surface area to this problem is going to be a headache. You guys ready for the headache?
No.
Cheers. I'll leave you here. The rest of this problem I've already taught you. Have a good day. I'm just kidding.
Rather take the headache than that.
You don't want to solve it on your own? Okay, so let's talk about this because now we should have the techniques to be able to solve this problem. I'll do the hard part. Ready? S of 2 pi root of 0 to 1 of e to the x root 1 plus e to the 2x, or e to the 2x dx. What should I do to make this problem easier for me? What technique would you do if this was a problem I gave you on the exam?
Is it U sub?
Sweet. Nice job, Brian. It is a U sub that we would do here. So the U is going to be what?
1 plus e to the 2x?
1 plus e to the 2x. Cool. So then we're going to get du is equal to 2e to the 2x dx. Is that correct, everybody?
Yes.
Oh, my bad. I made a mistake. I'm actually making the problem harder for myself. I don't want to do it this way. And why would I not want this to be my u? I'm glad I made the mistake, actually. Tell me why this is not a good u.
And then you'd have to do integration by parts, right?
Well, not only will I have to do integration by parts, if I clean this up, watch what happens. It's good to go down a wormhole sometimes. Isn't this e to the x times e to the x?
Yes.
So I would get e to the x dx to go. That would take this and this, but I would have an e to the x left.
So you really didn't get rid of it?
No, in fact, it becomes quite a headache. To solve for it, I'd end up getting u minus 1 rooted is e to the x. That's not cool. Does everyone see that? So then I'd have two u's, or two radicals. I don't want to deal with two radicals. So this is not the u that I want to use. What do you guys think I should use then?
Is it e to the x?
That's it. It is going to be e to the x. But I want to make sure that we're all clear. It isn't this e to the x. It's this one. Because, just so it's clear to you, it's s equals 2 pi integral from 0 to 1 of e to the x root of 1 plus e to the x squared dx. It's this e to the x that I'm going to use. So when I do the u sub, I'm going to end up with e to the x dx, but I'm going to have inside here 1 plus u squared. Do you see that? So my u, right, my u is, well, here, I'll erase that, I don't want that there, is that e to the x, du is going to be e to the x dx, this takes care of this and this. And so I'm going to get 2 pi integral of 1 plus u squared du. And I'm not going to mess with the bounds. I don't want to mess with the bounds. So I'll come back to the bounds in about 3 months. Okay? Now, 1 plus u squared, how would I attack this integral? What would you do, my friends? Any thoughts?
Would it be a trig sub where like the other time we attempted, it would be a x equals
That's what it is.
the 10?
This is a trig sub with tan. So now what's going to happen is I'm going to go u is 1 tan theta. My du is going to be secant squared theta d theta. I'm going to draw my triangle now, just so that we have it. Here's my theta. So it's going to be u over 1, and this is going to give me 1 plus u squared rooted. Oh, look at that. It's the integral there. So now, here it comes, my friends. S is equal to 2 pi square root of 1 plus tangent theta squared under the root, secant squared theta d theta, right?
Yes.
Which will then become secant squared theta d theta, but one's under the root, so that's going to become 2 pi secant theta secant squared theta d theta, which is going to be the integral of 2, what am I doing? That's S, not integral. Secant cubed theta d theta. And what's the technique of integration for secant cubed theta?
A lot of steps.
A lot of steps. Very nice.
It's refer to the notes.
It's a refer to the notes problem. This is one that I did with you guys, right?
Yeah.
It is a repeater, right?
Mm-hmm.
And so we need to know how to do this. So let's just say, all right, let's do it. How would I attack this problem? I told you. How many techniques have we already used? We've done U, we've done trig. Now we're going to do
Integration by parts.
integration by parts. It's a UV. So what's the U? What's my dV?
Seeking Q?
No, it's going to be broken up. So,
To break them up.
yeah, we're going to break
You
up.
should be secant then, right?
The U should be secant. the dv should be secant squared theta d theta. And the reason for that is the antiderivative of secant squared is tangent, right?
Yes, that's correct.
So then I'm going to get du is secant theta, tangent theta, d theta. V is going to be tangent theta. Yes?
Yes.
Yes. Yes.
Okay, the formula is u times v minus the integral of v du. See how I'm trying to take you guys through this journey so you guys can see, is chapter 7 important?
Keeps coming bad, like it keeps coming back like a bad nightmare.
Well, look, so far every technique that we've done except for the u sub is chapter 7. So u times v is going to give me secant theta tangent theta minus the integral of v, which is tangent theta secant theta tangent theta d theta. Right? And we shouldn't forget there's this big old 2 pi out front. So then 2 pi secant theta plus, oops, no plus, tangent theta minus, this is going to be the integral of tangent squared theta secant theta d theta, right?
Yes, right.
The technique here is to break this up, so I believe it's 1 minus secant squared theta times secant theta d theta. Agreed?
Agreed.
Those are the,
yes.
the trig things that we're going to get. And so we're going to get 2 pi. I'm just going to distribute the 2 pi now. Minus 2 pi integral of secant theta d theta plus the integral of 2 pi secant cubed theta d theta. Right? Am I right there? I want to make sure. That's minus, that's plus. That's correct, right?
And we have a repeater, don't we?
Exactly. So we have a repeater.
Wouldn't it be a minus secant cube theta? That way, when we add it to the other side, we get 2 secant cube theta d theta, or the integral
So
of 2
let me
secant.
see. My trig identity might be wrong. So that's where I never have those memorized. So let's make sure that I have it right. So we want tangent, so I'm going to divide by cosine squared, cosine squared, cosine squared theta. Yep, I have it wrong, so perfect. This is tangent squared theta plus 1 is equal to secant squared theta. So then tangent squared theta is secant squared theta minus 1. So I have it backwards. This is backwards. It's important. See, this is why when you do these problems, it's so important that you know your identities and how to derive them. Since no one corrected me, I was like, okay, I guess I'm right. Turns out I wasn't. Okay. So then this should be secant cubed theta plus secant theta d theta. Right? Oh, I forgot the 2 pi here. So remember, I'm going to rewrite it. It was secant cubed theta d theta, right? Was this integral? Oh, I should just leave the 2 pi out instead of distributing it. Yeah, I'm going to make my life easy. And I'll show you why real quick. This is going to be 2 pi then, the secant cubed pi. Or actually, let me just keep it out and then I'll distribute it at the end. Okay? Is equal to secant theta tangent theta minus the integral of secant theta d theta. But then that's going to add over there, so I'm going to get a 2 here, correct? But don't I know the integral of secant theta? What do we do with secant theta, the integral of secant theta?
Multiply by 1. But like secant theta plus tan theta
So
over the same thing.
right?
And then you said
I'll do it so you can see it. To do the integral of this, I'm going to go secant theta times secant theta plus tangent theta over secant theta plus tangent theta d theta. What's the step for this problem? How do I integrate this?
you said
U sum. And this is really what I'm trying to show you is how involved all of this is, right? So that's going to become secant theta plus tangent theta. What is the derivative of secant theta?
secant theta tan theta.
What's the derivative of tan theta?
Secant squared theta.
Correct. So then, going back to the problem, I'm going to get 2 secant cubed theta is equal to secant theta tangent theta minus the integral is going to be secant squared theta plus secant theta tan theta distributing over secant theta plus tan theta. Here's the d theta, and we can see that this is going to be secant cubed theta is equal to secant theta tan theta minus, now the integral when I do the u is going to be 1 over u du. The integral of du, or 1 over u, is ln, correct?
Yes.
And then we're going to put in what our u was, which was secant theta plus tangent theta. Oops, no d theta. Close the absolute value. And then we need to divide it by 2. So the integral of secant cubed theta is 1/2 secant theta tangent theta minus ln of secant theta plus tangent theta. But we need to remember something. Oh, this is like this. What was in front of secant cubed theta? Go all the way back. What was in front of the
2 pi.
2 pi. So now let's bring 2 pi back. So if I bring 2 pi back, oops. Sorry about that. I'm going to get pi secant theta tangent theta minus pi ln of secant theta plus tangent theta. But now we got to go back to the triangle. Are you guys okay?
Can you go up a little bit?
Sure.
A little bit more, please. A little bit more.
I don't have any of this work on my notes. I'm doing it all right now for you. That's why I made the mistake with the trig. I'm just doing
Because shouldn't it be plus? Well, I don't know if I copied it down wrong, but shouldn't it be plus ln secant theta plus tan theta?
Where are you talking about?
Plus sign in front of the integral of secant theta d theta.
You're saying here?
Where did you get your minus sign from?
For this?
That minus sign.
So when I did the distribution, this should have been a plus. Yeah, I believe that should be a plus. Plus. So it's a plus, and plus. Yep.
Okay.
Thank you.
Mm-hmm.
When I made the mistake, I didn't change it on that one piece. So, like I said, I'm doing this all off the top of my head right now. Okay, are we okay to this point?
Yeah.
I'm trying to be deliberate with this problem and show you every step. Because if you don't see every step, it's, especially if you just look at the book, they're like, oh, from here to here. But there's so many different techniques to this problem that you can see how much of a can of worms this problem can become, right?
For sure.
Okay, so the triangle that we had, because we need the triangle, if you all remember, was u over 1, right? So it was this.
Yeah.
Here, I'll take you back to it's this, from the trig sub that we did. Because we're still in the world of trig subs. This is just an integral within the trig sub integral. Okay? So now, I need to put everything back in terms of, from the trig sub, I'm going to put it back in terms of u, so that then from the u, I can go back to in terms of x, in terms of the e to the x. So you see, there's integral with an integral with an integral of this thing. So here we go. So now, it's going to be pi, what is secant theta? Isn't that hypotenuse over adjacent?
Correct.
So that should be 1 plus u squared. Tangent would be u plus pi ln of 1 plus u squared plus u. Agreed?
Agreed.
Okay.
Yes.
Now, to put it in terms of what u was a substitution for what? at the very beginning.
Secant theta.
Ooh, even more beginning than that, my friend.
E to the x.
E to the x. See, with this type of problem, if you don't stay super organized, I mean, look at this problem. There's 1 page, 2 page, we're on the 3rd page. We're gonna go into a 4th page to do this problem. It's e to the x. So I'm gonna get root of 1 plus e to the 2x. In fact, let me write it so it's cleaner for you. I'm going to go pi e to the x 1 plus e to the 2x plus pi ln of root of 1 plus e to the 2x plus e to the x. And now I can evaluate it at its bounds. What were the bounds for this problem at the very, very beginning?
0 and 1.
0 to 1. Okay, so let's do it. So I'm going to get pi e to the 1 root 1 plus e to the 2 plus pi ln of root 1 plus e to the 2nd plus e to the 1 minus pi e to the 0 1 plus e to the 2 times 0 plus, this becomes a minus, right, because I have to distribute the negative, minus pi ln root 1 plus e to the 2 times 0 plus e to the 0 agreed?
Agreed.
Which is going to give me pi e root 1 plus e squared plus pi ln 1 plus e squared plus e minus pi root 2 minus pi ln of root 2 plus 1. Finney. How many techniques were used in this problem for integration? I believe there was 4, correct? Thank God I'm recording this. You should probably watch me go over this problem a few times, because the techniques that will be involved, you're going to have to ask yourself question after question about how to attack this type of problem. Do you want me to walk through this problem again so you can see it?
If you wouldn't mind, that'd be helpful.
All right. Has everyone copied down the problem? Are you
You
guys
already
good?
have posted.
Yeah, I finished copying it.
Right?
Okay, so let's go through this. Take you through the journey of this problem, right? So the very first part isn't too bad, right? So we have to decide, since we're trying to find the surface area, what the radius is going to be. And so the radius, since we're rotating about the x-axis, is how far we are from the x-axis to our function. So we know that that radius is going to be, or the radii along that whole interval from 0 to 1, the radii are going to be a y distance height, right? Or a y distance length from the axis of rotation. Yes?
Correct.
Okay, so that's going to give us the y radius. So when we set up the problem, we know that our problem should be, and I'll do it in a different color just so you guys can see, it should be 2 pi y, that's our circumference, ds. And then we need to remember that our ds is decided by the bounds, right? By our bounds. And since our bounds here are x's, we have to be in terms of dx. Yes?
Yes, correct.
Okay, so then from there, my integral is going to go from, okay, it's going to be from 0 to 1, 2 pi y, the arc length formula that we have, dx, right? This is the equivalent of ds. Yes?
Yes. Yes.
Y is equal to e dx, so we do the substitution, we do the derivative, that gives us the e to the x, and then we need to square it, so this is the integral that we have. In cleaning it up, we end up with this situation here, and we need to decide how to attack it, right? So here, the very first thing that we do is we know that, I mean, we could have tried to do a trig sub here, but if we would have done a trig sub here, look at how ugly it would have been. I think Rodney was the one who suggested a trig sub here because it was 1 plus something squared. But you got to think of it. It's x is equal to tan theta, right? But my x in this case isn't x. It's e to the x. So
Yeah, that definitely changes the
complexity.
Attacking.
Yeah, the complexity here is so much greater, right? Because what ends up happening is we would have gotten e to the x dx is equal to secant squared theta d theta, which could have been something that which would have worked, because the e to the x, this e to the x dx would have taken care of this, and then we could have gone and attacked the problem. It just, most people wouldn't see that, right? In terms of complexity. But it would have worked. It's just, how much do you want to deal with the complexity, right? Does that make sense what I'm saying?
Yeah, I see it.
And then your triangle for this would have been a triangle that looked like this. It would have been e to the x over 1, and then you would have had your 1 plus e to the 2x rooted, which would have worked, but I just didn't want to do it that way for complexity reasons for the rest of you. Okay? So if you feel sophisticated enough, you could have attacked it that way. It's just, I didn't want to lose people on the way. So then once we have this, then we did do the trig sub, and we ended up with this crazy worm, right? This wormhole that we fell into, where I even tried to set it up for you guys so you could see 1 plus the tan squared, secant squared, that became the secant squared under the root, which became secant cubed, and then this one here we've taken for granted. Had we had our class live in a classroom, I would have had you do this problem on an exam, meaning this one, where I would want you to know how to do this super quick. So in terms of the difficulty of this class, no, it is not as hard as it would have been had you been in my class live. Because these are problems that I would have expected you to be able to do on an exam. And I would have embedded them in problems like this. Okay? So why am I telling you this? It's because I want you to be aware when you guys go to Calc 3 and they build on this material, you should be able to do this material. That's why I took the time today with this. Does that make sense?
Yeah, we appreciate that.
I mean, my job is to teach you, right? Like, the grades you get, those are your grades. But to make sure that you know the material is something that it matters to me because I love this subject. I've spent my life doing this subject. And so I want you guys to be able to see it. And then I wanted to spend some time really delving into the problem so you could all see it. So what I did here is I took the 2 pi out just so that I could do the problem. Knowing that it's a secant cubed, I knew that it was going to be integration by parts. So we did a u, then we did a trig sub, then we're doing an integration by parts. Thank God I didn't do a partial fraction decomposition to you. And then we went through the process of doing the integral, coming down. Always important to have the right identity. Did you guys see how I generated the identity so I knew that I was wrong so I could fix it? Did it make sense, the side work that I did there?
Oh yeah, the side work makes sense.
Okay, because all I did is there's only one identity I know. I only know sine squared plus cosine squared is equal to 1. I generate all of the other ones. I mean, I got a lot of math in my head, but sometimes it's just better to be able to confirm it and generate it than it is to just have it memorized. And so I want to remember my kids' names. And so I remember one identity and delve from there. Then we find that it's a repeater. The repeater comes over and I get my 2 dividing by 2. I ended up, I even showed the work for the secant when I had this. After I did that, I showed the work for the secant so you guys could see the u sub of the secant that was in there. And the secant's u sub. Jeez. I really went thorough on you guys. And then I divide by 2. Getting that. Then I brought the 2 pi in from the original part of the problem. These are multiplying. I should put a product there so you know. And then from here we end up here. Now, once I was back at the trig, I knew I needed the triangle to attack the problem, right? Drawing my triangle, I broke down what secant tangent was and embedded them. And then I had to remember, all right, it's u. I need to change the u back to in terms of the e to the x. And then what were my original bounds to be able to solve the problem. And then once I did the bounds, it's just algebra at that point. This is probably the most complicated problem we've done in this class thus far. That's the surface area. Isn't that so satisfying?
I wonder I have a headache.
Okay. Are there any questions on this? Does the setup for the surface area make sense?
Yes, it does.
Okay. The integration piece is going to be a little bit tedious. The next time we meet, we're going to go into differential equations. It becomes so much easier, guys. We'll do 9.1 and 9.2 next class meeting. And then we'll do 9.3 and 10.1 next Wednesday. And and then we'll have the test the following Wednesday after that. So 2 Wednesdays from now, we'll have our exam on chapter 8 and 9. But chapter 9 is not bad at all. Especially if you had me for Calc 1, where I dealt with differentials with you in detail. That will be helpful. All right, I'm going to stop recording and then just see if you have any questions for me.